Hi, I'm Tony Bronars,
And I'm Young Park.
and we are here to present our final project studying tactile feedback for industrial insertion tasks. Insertion tasks, commonly found in modern manufacturing settings, involve complex contact dynamics. Since it requires such tight fit to succeed at the task, actually feeling how things are grasped in the fingers becomes much more important for a policy to succeed. Tactile feedback allows the policy to reason about how things are grasped within the fingers and the actual contact happening between the connector and connector holes. Then a natural question arises. What kind of tactile sensor should we use? There are two types of tactile sensors in the community. First is a camera-based sensor, which is basically a near-field camera located underneath the gel pad, recording its deformation. We can get high-resolution readings of contact geometries for a relatively cheap price. Second is pressure array sensors, which is a fixed array of pressure-sensing taxels attached to an electric board. These sensors give us pretty compact representations of contact states at high frequency, but it can get relatively expensive depending on the resolution of readings. Within those categories, there are also different ways to represent the raw readings of these sensors. For camera-based sensors, for instance, there's a choice of using the raw RGB image recorded from the camera, but one can also extract the depth of the gel deformation and use that as the tactile representation. One can also use gel pads with unique marker patterns on them, where we can extract the optical flow of such marker fields for a more compact representation of contact states. For pressure array sensors, things are more obvious. While some expensive sensors give you the full XYZ forces with normal and shear for each taxel, one can go with the more cheap sensor that only gives you the normal force, or one can go with the most basic sensor and simply tell whether something is in contact or not. Among all these device types and ways to represent the tactile readings, we aim to answer the question, which tactile sensor and representation is best suited for industrial insertion tasks? In particular, we have compared these 5 tactile representations. To do that, we trained a policy with behavior cloning for a standard PEG insertion task included in the NISC board environment. We used Franca Panda with fingers each attached with gel site and Zella sensors, each representing camera-based and pressure array tactile sensors. For both tactile sensors, we've collected 50 demonstrations of inserting a PEG with random initial states around the hole.
We have recorded all tactile readings for both fingers, in addition to the other relevant observation modalities, such as current gripper pose and commanded gripper pose. Using the recorded dataset, we trained a policy using conditional VAE, predicting a sequence of actions based on current observations. During training, the decoder is trained to predict the future action sequences from tactile readings, current gripper pose, and style it in predicted from the encoder. Then, a straightforward beta VAE loss is applied as an objective function. We used beta 0.1 in all our experiments. Finally, we have evaluated each policies by rolling out 10 times and recording its success rates. This is the result. For a policy that only operates on tactile readings, you can first observe that pressure array sensor with full XYZ force has the highest success rate. This indicates that information about shear forces within fingers plays a critical role in succeeding the task, which is also evident from the fact that the policy completely failed to complete the task when operating only on normal forces. Both marker RGB readings from gel site and extracted optical flow showed reasonable non-zero success rates, but not as good as the XYZ force readings from the pressure array sensor. We observed little or no benefit of adding wrist camera as an additional observation modality. Here are some actual videos of policy rollouts. These success videos show that the policy is leveraging the tactile information to reason about the grasp within the fingers and adjust its behavior accordingly. However, there are some interesting failure cases as well. In this video, we can see that the policy got stuck in the middle of its execution, where we had to manually perturb the state to make the policy complete the task. This video shows the policy quickly getting out of training data distribution and does not know how to recover from that state. In terms of training, we noticed that dropping out certain modalities of the observation can prevent the policy from simply memorizing the motion based on its gripper state, allowing it to attend more on the actual tactile readings during its execution. To conclude, these are our final remarks. We have learned that information about shear is crucial for insertion types of tasks. However, we here note that the results will differ based on the behavior generation method used to train a policy. The conclusion might change, for instance, when one tries to learn behaviors with reinforcement learning, not behavior cloning. If one considers training things in simulation, the aspect of simulating these tactile sensors also comes into play. We hope our findings are helpful to the community considering tactile sensors for industrial insertion tasks. Thanks for watching.